I want to create some target-seeking rockets, and as a challenge, I decided I'm limiting myself to the genetic algorithm. It's been done before by some very fantastic people, but I wanted to mess with it myself and try a few things. What I first tried is this. Imagine if there's a rocket, and there's a series of angles. We go through the angles one by one, and for each angle, the rocket moves towards the direction of the angle. After a certain number of frames, you pick the rocket closest to the target, copy its angles to a bunch of new rockets, and adjust the angles slightly for each rocket as a mutation. These angles are the genetics of each rocket that we use to find the best path. I made the rockets moving points for obvious reasons. Now this didn't work. It didn't work for a couple of reasons. First and foremost, the fact that the distance to the target is not the best thing to use when you want to measure the best path, especially in cases where the path requires you to go backwards even a little bit. It's hard to find another way to choose the best rocket in each generation, but I think I have some ways to make this better without having to do all that. What if the angles aren't directions to move? Now they're how much and in what direction to steer. It's a small but very effective change. As problematic as the way we choose the best rocket still is, this way the movement will be smoother and generally work better. And that looks something like this. It's much better than the last algorithm. It succeeded pretty easily and found the path to the goal pretty quickly. It did this for the first map. And it did this for the second map. But it failed for the third map, and it's not surprising. The genetic algorithm has a lot of utility, but it isn't the most useful unless combined with other machine learning algorithms. By itself, it's pretty weak. The things you can do with it aren't that fancy, but there's one more way to get this thing to finish the third map. I tried a couple of things like averaging the values of the angles in hopes of getting a more smooth flight, but it didn't work, which makes sense. If you move the angles towards the average of all of them, you make all of them the same. And when you make all of them the same, seeing as every angle is steering, you constantly steer in one direction, so you just end up rotating in place. This was easier to program than I thought because I actually remembered how to write some clean code for once, thank God. The final thing I tried, which worked wonders, is batching. The main problem with the algorithm right now as it is that when we find a path that's reasonable, we keep changing the beginning of the path. The beginning of the path doesn't need to change. We already found what the best angles are at the beginning. The way you solve that problem is with batching. You run the algorithm with higher randomness and a shorter runtime. Once it finishes the first batch, you just add the path you found to the starting path of every rocket. This worked wonders because, like I said, it solved one of the main problems, which is that once you found what's optimal for a certain amount of time, you don't need to change that again. This way, the optimal solution you found for, say, the first 3 seconds of the simulation stays what it is and it doesn't change with every mutation. The genetic algorithm by itself is still not the best tool for this job, but with batching, it's much more powerful. That's how I managed to beat all 3 maps I made for myself. This took a while because I have some other cool things I want to try that are going to take a lot more work, and I've actually been focusing on those. So subscribe if you like my content, and don't forget to like the video if you enjoyed it.